So multiple linear regression is something which many of you have encountered in statistics. Now we are going to look at it from data mining perspective, how it's used and how it's different from what we have learned in statistics. Now, what regression models do is it is creating a linear relationship. So it's a multiple linear regression. So therefore, it's a linear model where outcome Y, it could be anything. It could be the price of a product, it could be revenue, it could be cost, whatever it might be. It's a function of several predictors. It could be, for example, the price of a product is a function of the weight of the product, energy efficiency of the product, etc. So X1, X2, all the way till XP are predictors which are predicting what the price should be. And there's a coefficient that we get for each of these predictors, and that tells us how strong those predictors are impacting the price. And then there's an error. All those things that we are not able to account for using these variables go into the error term. So it's called the noise or error. This is what the linear model does. And in regression, the objective could be either to explain the data or to predict. In statistics, we learn explanatory modeling, where we look at the relationship between predictors and the target. All these predictor variables and whatever the target variable is, the price, for example. Here, the objective, the goal is to fit the data well, right? That's why we look at goodness of fit or R square, high R square values and all, P values, residual analysis. Many of these things are very important in explanatory models because our objective is to ensure that whatever model it is capturing the current data very well. The other objective that we could have fulfilled with multiple linear regression is the predictive modeling. Now, here the goal is somewhat different. Here we are not interested in explaining the current data. Here we want to predict target values in other data sets, something different from what we have trained the model in, where we have a predictor value, but we don't have the target. We know what these different parameters of the product is, but we don't know what the price might be, for example. This is the classic data mining context. Here we want to optimize the predictive accuracy, right? So here we are going back to our previous discussion of evaluating performance of a data mining model. Here we are interested in reducing the error in our prediction of this new record, which we have not seen yet. So we do the same thing. We train the model on training data, but the assessment of the performance is done on the validation data. And we are not necessarily interested in explaining the role of these predictors. That's not the goal of these models. Although it's important to know what these predictors are doing, it's always helpful to understand how the weight might be increasing the price or decreasing the price, etc., because that gives us a context of that situation, but it's not the primary objective. Now, the main differences in using a linear regression is between the explanatory model and predictive model is that a good explanatory model will fit the data closely, whereas the predictive model will predict new records accurately. So that's one big difference. And this difference actually can be impacted by which variables we are going to choose as predictors. A model which does very well as an explanatory model may not necessarily do very well as a predictive model. So the choice of input variables as well as their forms, whether it's a linear or logarithmic or whatever other forms, they could differ between the two types of models. Now, in explanatory models, we typically use the entire data set because we want to capture the essence of the whole data set and create a model, linear model which captures whatever is going on in the data. And the objective is to find the best fitting model, and we can then use the hypothesized relationship between the predictor and the dependent variable and make assessments of how strongly associated they are. In predictive models, we don't use the whole data. We split the data into training set and validation set, like I mentioned earlier. And the training set is used to estimate the model. Validation set is used to assess the predictive performance of the model. So that's where we predict how well it's done. Performance measures for explanatory models will measure how close the data fits with the model and how strong the relationship is between all these different predictors we are using with the dependent variable, right? But in predictive models, we are looking at only the prediction for new records. We are not interested in how well it fits the model or how strong the relationship is among these variables with the dependent variable. So in a sense, in explanatory model, our focus is on these coefficients, which we just saw in that equation. So we are interested in the betas, whereas in predictive models, our focus is on predictions. So the hat, which you say y hat, whenever we put a hat on top of the y variable, y is your predicted variable, the dependent variable, hat indicates this is your predicted value, whereas without a hat, it's the actual value, right? So we want to know how well we are predicting the y hat. So that's something which is the objective in predictive models. Now, how do we estimate the regression equation? How do we predict? Suppose we have identified the predictors for which we need some contextual understanding. Right? Most of the time in business context, when we are trying to determine which variables will impact something, whether it's revenue, whether it's profitability, or price of a product, or whatever, or which customers to target, for example, the predictors that we're going to choose are typically based on domain knowledge. You need to have the domain knowledge and use that domain knowledge to decide the right predictors. Then we estimate the coefficients of the regression formula. So we run the model, we determine what the betas are and what the values are. And essentially, the goal of any linear regression is to look at all the data points that are there in the data set. So this is a very simple example. It's not a multiple linear, it's just one variable, experience and salary, right? So if it's multiple variable, it'll be a hyperplane rather than a simple XY axis here. So if there are several data sets we have between experience and salary, the linear model is typically trying to create a straight line that passes through these different data sets that exist and try to minimize the distance between each of these data points from that line, right? So that's the goal of a linear regression, sum of squared deviation. The deviation will be the distance, and it's looking at the sum of the square deviation for all of these values from that line. That's the goal of it, and based on that, it predicts different coefficients. Again, predicted values are given as the hats here. So to predict the value of outcome variable for a record with the predictors of x1, x2, all the way till xp, we use this equation. So y hat is our objective, which is predictive models. Say objective, we are trying to find y hat. For that, we will have a model where everything will be with a hat here, which is a predicted value for each of these coefficients for any new data that we will have in the validation set. Now, some of the assumptions that we have to keep in mind when we're using multiple linear regression are, number one, we assume that the error that we saw, the epsilon, one of the variables that we see in this model is this epsilon, which is the error. This error is normally distributed. This is one of the assumptions that we have in linear regression. The second assumption is that the choice of predictors and their form is correct. We are assuming that we know the domain. We understand that the relationship between y and these x's, linear relationship that we are talking about, is correct because of our understanding. We also assume that these records are independent of each other. So customer one, customer two, customer three, if we have all these different customers in our data set, they are independent from each other in how they take decisions. And then fourth is the variability in the outcome values for a given set of predictors is the same, regardless of the value of the predictors. So if we were to use predictors, like I said earlier, price of a product is dependent on the weight of the product or energy efficiency of the product, we are assuming that there's a homoscedasticity, which means that whether we were to use high weight products and the variance in that case, the variability in the outcome in those high weight type of products versus low weight type of products, the variability in the outcome, they will be similar. It's not like systematically there's high variability in the price of the products with high weights versus products which have low weights. So we won't have this assumption that the variability of outcome variable is not changing depending on the values of these predictors. They're randomly distributed, and homoscedasticity is what you call this. So some practical approaches in the case of data mining and predictive modeling, the good thing is many of these assumptions don't matter as much. In explanatory model, all these assumptions are extremely important. But if we are doing predictive modeling, even if we drop, let's say, the first assumption, that is the error, or equivalently the outcome variable y, if it's not normally distributed, we still would have, we could get a good model for prediction. It's not a must for a good predictive model to satisfy this assumption. So it's required for explanatory modeling, but not for predictive modeling. So that's a good sign. At least it gives us more flexibility. And in fact, the other assumptions also, some of the assumptions that we have here, if they are violated, it is still possible that whatever model we got, the multiple linear regression model, will result in predictions that are sufficiently accurate. And so we are still okay with the kind of accuracy we are getting with the model that we created, even when some of the other assumptions are not valid. So this is something which is true for predictive modeling. We are a little less sort of rigid in terms of the requirements of meeting all these assumptions. The key in predictive modeling is to evaluate the performance, like we talked about in the previous set of discussion on evaluation of predictive performance, whether that performance is good enough. And satisfying these assumptions is always secondary interest. We can always look at residual analysis to understand potentially improved models. So that's an important part to capture. So here, again, going back to the model, the data that we have used earlier also, the used car sales and all that, the rental company, which is the Toyota Corolla CSV file. We are predicting the price of used Toyota Corollas based on their specification. So every car has specification in terms of the age of the product, whether it's automatic or not, what color it has, etc. So we're trying to predict the price of each of these cars based on these specifications. And let's say we have prices of 1,000 used Toyota cars, as well as their specifications. So we are interested in predicting the price. So these are the variables. Price is our dependent variable. Age, kilometers that it has in odometer. The fuel type that it has three possibilities: petrol, diesel, or CNG. Horsepower of this product, metallic color or not, automatic or not, cylinder volume in cubic centimeters, how many doors it has, quarterly road tax in euros. And this is external characteristic, right? This is not based on the car specific variable, but this is external factors that could influence the price of the product. And then weight. So weight is in kilograms. This data sample is just giving you a snapshot of how the data looks like. For each of the price, you have different age and all those things. Now notice that fuel type is a categorical variable. As we've got three types: petrol, diesel, and CNG. So it's very important to first convert this variable into dummy variables. So for fuel type, if you notice, the data is currently having diesel, they're listed as diesel, petrol, CNG, etc. But we'll have to convert that into three columns. Fuel type petrol, which will be 0 or 1, depending on which case we are looking at. Fuel type diesel, 0 or 1. And the third one will be CNG, 0 or 1. But the third one is redundant. We don't really need the third one to analyze any model, because these first two automatically gives us an understanding of what the third one will be. So this again goes through the pre-processing like we talked about in the previous, the first lectures that I had posted. We have to pre-process the data, and then we have to fit the regression model. So basically there's a code. Again, I'm not going into the coding in our lectures, but it's something which you will be able to familiarize yourself when you are aware of the programming language. But also today, most of the generative AI helps you understand, what is the way this is working. So I would highly recommend you to code yourself these things and try to understand the mechanics behind it. So we are choosing certain predictors. We have an outcome of price, but to start the model, we have to convert some of these variables into dummies. So that's what we're doing here. Not all variables will be converted into dummies. Only the ones which are categorical variables will be converted into dummies. And this is the outcome variable, y. The next line is basically trying to convert the data into training set and validation set. So train X, valid X, train Y, valid Y. So what we are doing is splitting the data into 60% and 40%. Right? So 40% of this will be in the test, which is a validation set, and 60% will be the training set. That's what we have done here. And this is the code we use for train test split. We can split the data this way. And then we run the regression and fit the model on training set. What we find is that this is the performance that we get. These are the predicted coefficients for the training set. This is the performance of the regression statistics. You can see mean error is 0. Notice that this was a training model, so we would expect low errors in this case. But the key is to find the error in the validation set, right? Performance of this model in the validation set. So we do the prediction for validation set. So now we are predicting the validation set. Again, the code is there. Here we are trying to predict the valid set. And we look at the values. So predicted value, let's say $10,607, where the actual value was $11,500, the price of the product. Predicted value was $9,272. Actual was $8,950. So for each of them, we have an error or residual that we can calculate, the difference between the two, actual minus predicted. Values, these values then can be something which we can take into account. And then we also can look at the performance measures for this validation set. And we can see the mean error is not 0 anymore. It is going to be different. But overall, if you look at mean absolute percentage error and other metrics, it's not a bad outcome as compared to what we had here for training set. Right? So it's predicting relatively well for the validation set, so which is a good sign. So that's something which is what we can also take into account when we are going through this model. Both of these training set and validation set results. Now we could use some histograms are always very helpful. I've shown that earlier also in the previous discussion on evaluating performance. The residuals that we just calculated in that slide, which includes actual and the predicted values, we could plot those residuals in a histogram, and that can give us a lot of information about what's going on in this data. Right, so those residuals that we just had calculated earlier, with all those residuals using certain code, if I plot a histogram, which is over here, we can see that most of the errors are between plus and minus $2,000. Right, so we are not predicting correctly in that range most of the time. And then another observation that we see is that there is large positive residuals. So there is this set. So we are under predicting price of certain cars a bit more, like over here. So there is that also, which large positive residuals indicate. So these the actual prices are very high, and we are predicting much lower than that. So this is helpful and can be of concern or may not be of concern depending on the application. So we need to be able to look at these and reflect on these kind of things. Now, linear regression, as we know, basically tries to predict outcome with different predictors, which means that sometimes we would want to use as many predictors as possible. We would like to use too many predictors and make sure that we are accounting for everything. But the goal is typically to find a parsimonious model. Parsimonious means use as less of predictor variables to capture as much of the variance in y and predict as much of y. Right? So simplest model is typically the best, and therefore we often want to select a subset of predictors rather than using everything, because having a parsimonious model can be more robust and better accuracy also. And oftentimes it's also about the bias and variance trade-off. Having too many predictors versus less predictors, one increases the bias, other increases the variance, and there's a trade-off between the two. So we want to ensure that we only use those variables that matter rather than everything, and drop others, so that our prediction variance can be reduced. Right? So we are ensuring that. There are many ways in which we can do this, finding a subset of predictors that matter. The first one is exhaustive search, and then there are others which are forward selection, backward elimination, and stepwise regression. Right? So there are these basically the two types: exhaustive search or partial search. And in partial search, we have three types: forward selection, backward elimination, and stepwise regression, to find which predictors should we use and which we should not use. Now, exhaustive search, as the name suggests, is basically looking at all possible subsets of predictors. So if we have, for example, three predictors, we will try to look for each of them individually and then each of their pairs. So 1, 2, 3, then 1 and 2 together, 1 and 3 together, 2 and 3 together, and then 1, 2, 3, all of them together. So we are looking at all possible combinations of the predictors and then determining which one results in the best outcome. Now, as you can see, if we had just three, we have quite a few combinations to worry about. And if we have several predictors, which is what typically happens in real world scenarios, the situation can sort of become very complex. It will be computationally intensive. For big data, it will be not feasible. Normally, when we are trying to assess, we will use this metric called adjusted R square, which you may have heard before in statistics classes also. So it's different from R square. R square looks at the variance of the Y predicted by all the X's. Adjusted R square puts some penalty of how many predictors you're using. Too many predictors, it reduces the R square a little bit. It adjusts the R square to a little lower value as you keep on increasing the predictors. So this is something which we will be looking at along with some other metrics to understand which subsets are worth using and which one we can get rid of. So as I was saying earlier, that this is computationally intensive. So if we have only two variables which are predicting our outcome, for this we will need three different searches, right? One with each of them individually. So if, let's say, we have variable number 1 and variable number 2, which are predicting our Y variable. So we will have one model which only includes variable 1, the other model which includes variable 2, third model which includes both of them. So there are three possible models for which we will have to do an exhaustive search and determine which one works best. If it's three variables, then it again increases in magnitude. I talked about that earlier also. With four variables, even further. So essentially what happens is it grows quite fast in terms of the exhaustive search, number of models that we will have to search. Typically, it grows at the rate of 2 raised to the power n minus 1. So if I'm looking at four variable case, we have four variables, it'll be 2 times 2 raised to the power 4, so which is 16 minus 1. There will be 15 different possible models which will have to be searched, and we will have to determine which combination actually works best. So that's one thing which we need to be aware of, that exhaustive search looks at all possible combinations, but it also is computationally intensive. We use adjusted R square. I already talked about that, but there are also other metrics like AIC and BIC. Along with adjusted R square, these two metrics also help us understand how well these subset of variables are predicting the outcome variable. Now, adjusted R square, higher is better, right? The moment you start reducing those adjusted R square, we know that those extra variables that we're adding is not worth it. Our model is becoming less robust. In some sense, we are adding these predictors unnecessarily. AIC and BIC goes the other way around. The lower values are better, right? So lower values for AIC and BIC are better. So as the AIC and BIC are continuously going down, we keep on adding predictors. But if it starts to go up, then we stop adding predictors. So we look for AIC of one model versus the AIC of another model, or PIC of one model or R adjusted R square of one model. Typically for AIC, a difference of more than 10, this is a rule of thumb. It's a strong indication that one with the higher AIC is not the best model. So a difference of 10 is like a rule of thumb. Now, I've provided the code. I'm not going over all this. The thing which I want to mention is that exhaustive search, as well as the partial search, whether it's forward, backward elimination, or stepwise regression, all these you don't get them as part of the Python package. Right? So the SC kit does not have them as part of the libraries. So you have them as part of the DMBA package within which you have exhaustive search. So I have to pull that, I have to call that. And likewise, I will have to do that for backward, forward, and stepwise regression. So this is something which I have provided in this, like how you call it. But if you are yourself, I mean, those who are more programming intensive and want to learn how that exhaustive search works, I've also provided exactly what's going on in the exhaustive search within the reading. You'll see what that library does. How is it defined? So you get to see that also. So this code is what you run. I'm not going over the code, but essentially, um, after running the model, what we are going to see is a set of number of variables that we are including in the model, right? 1, 2, 3, 4, how many variables we're including in the variable model. And then for each of them, we see what is the R square, adjusted R square. Is it increasing? Is it decreasing? And what is the AIC? Is it increasing? Is it decreasing? So you can see that our R square, adjusted R square, is increasing until about this point, until we add 8 variables. When we add the ninth variable, it starts to go down. So 0.8542, 0.8541. So it's going down and further down, etc. So 8 seems to be, according to adjusted R square, the number of variables that we want to include. And if we go by the AIC also, we can see lower is better. So it's reducing in numbers here, 8984, 8893, keeps on going down until we are at eighth number of eight variables here, 8712. But when we add the ninth variable, it becomes 8714. It increases. So again, both of these metrics are adjusted R square and AIC suggest that we should use 8 variables. And we also know which variables to use. We can identify them also using the model itself. So we will know exactly which are those 8 variables that result in the best outcome. And the same thing now, instead of exhaustive search, which is computationally intensive, we could do with partial search. And there are 3 ways to do it. Backward elimination basically says that you first put all the predictors in the model, and then you successively keep on eliminating the least useful predictors, the ones which have very low coefficients. You keep on removing them one by one and stop at the point when you have all the predictors that are statistically significant in terms of the contribution. Right. So that's sort of backward elimination model. Again, a code which includes that package from where you're importing the backward elimination. You get your regression statistics here, and it tells you how many variables it has used and which are those variables. So age of the car, 1, 2, 3, 4, 5, 6, 7, 8. 8 variables, right? So those are the 8 variables that it's using, which matter for this particular one. Now, forward selection goes through a different partial selection approach. Instead of using all of them to begin with, you start with no predictor, and then you add one by one. Right? So in the backward elimination, we put everything and start removing. In this case, we don't put anything and start adding one at a time. And then ensure that the one which has the largest contribution are the ones that are remaining, and the ones that don't have, we keep on removing. And we stop when the addition is not statistically significant, right? So after a certain point in time, we will find that certain variables don't add anything to the model. So we stop at that point in time. So that's forward selection. Again, there is a model for it, have been provided to you in the reading, and you may want to go through this. And this also results in an outcome which we can take a look at. And we see that in this one also we have 8 variables, same 8 variables. So in some sense, it gives us confidence that whether we are using the exhaustive search or we are using one of the partial searches, the same set of variables are proving to be important. And that's those are these variables, and that is what we will be considering as important ones. And stepwise regression is a third partial model, which is like forward selection, but every single time when we are going through adding this new variable, if it's non-significant, we keep dropping them. We don't use them again in the next model, right? Again, for this also, we have to use the stepwise selection um, library in this package. And that helps us know which variables, again, the same set of variables. So in this particular example, at least with the data set we are using, whether it's forward selection, or backward elimination, stepwise regression, or exhaustive search, all of them result in the same set of 8 variables. Now, remember that these 2 variables are actually dummy variables, right? So this is fuel type diesel, fuel type petrol, and these two are compared to fuel type CNG. So these 2 variables are essentially part of that one single categorical variable, but divided into now 3 dummy variables. So those two are important because it captures how much more does the price of the product go when it's a diesel compared to CNG, how much more the price will be if it's petrol based as compared to CNG. So both of these are compared to CNG. Along with the models or the type of approaches that we just talked about, exhaustive search or partial search, there's also another type of technique that we can adopt, which helps in choosing the right subset. It's an alternative to all the things that we just talked about for subset selection. It's called regularization or shrinkage. So um, we are using in this particular technique, what we do is we penalize the coefficient's magnitude. Whatever the magnitude is, we put some penalty to it. And the reasoning behind this, considering the magnitude of beta hat coefficient, is that if there are highly correlated predictors, they will typically have high standard errors. Um, uh, then small changes that will happen in the training data will basically shift uh, which of these correlated predictors gets emphasized. So we want to identify those which have high standard errors, and then eliminate them based on a certain penalty that we want to put for these coefficients. So the overall approach that we are doing in this is looking at these coefficients, we are penalizing them and shrinking those coefficients, and reducing their variance. And by doing so, uh, those predictors for which these reach to zero, the coefficient reach to zero, we drop them. So the way it typically works is that there are few techniques that we can use. One is the ridge regression, other is Lasso. These are the two more commonly used regularization approaches for regression. It's called ridge regression or Lasso technique. And then there are other sort of closely connected, closely related type of techniques for this shrinkage. One is called Lasso CV, and the other is called ridge CV, basically using cross validation, and then Bayesian ridge. So there are different techniques, and the good thing is that we have these libraries available in Python, so very very easy to do these kinds of analysis and find the right subset. So what happens in ridge regression is, in ridge regression, we put penalty, as I said earlier, on the coefficients. But the way the penalty is put is by looking at the sum of the squared coefficients. So all the coefficients that we have, so there are p predictors, we are using p predictors. For each of them, we get a coefficient. We square them, and based on the sum of the squared terms, we are going to put some penalty, depending on what value it is. So it's called L2 penalty because it's a square term. Lasso uses absolute value of the coefficients. The p predictors, each of them have a coefficient. So we take the absolute value of those p betas and then sum them. And based on the absolute value, we put some penalty. So that's the basic approach that is different between the two. So here in linear regression, typically we are estimating the the sort of model by minimizing the training data sum of squared errors, right? We talked about this, that we're looking at a single line which reduces the error between the points and that line. Ridge regression and Lasso, they are trying to minimize the training data sum of squared error, similar to linear regression, but there is also an additional aspect which is subject to a penalty term. And we decide a threshold at which we decide that there should be a penalty. So we have that additional aspect added to it beyond what we typically have in multiple linear regression. So this threshold can be either set by the user. So we could decide what that threshold value is depending on the context, or it can be chosen by cross-validation. That's where this Lasso CV and Ridge CV technique come. When we say cross-validation, basically what it means is it takes subsets of data and tries to run the model and determines what is the right threshold value depending on those subsets. So by using these techniques, we can look at the optimal value for the penalty parameter, or we can ourselves provide a parameter in the model. And then Bayesian Ridge is a different technique, which is also an iterative approach where we use the whole training data set and derive the penalty parameter. So these are, again, things that we have. I have run these models in the readings. You'll see there are slides for them, which include also the output that you get from each of them, along with which variables these are indicating that we should be using. So I would highly recommend that you go over them and try this. You have assignment 2, which covers some of these topics, and you'll have to do some of these analysis in that as well. So with that, I think I'm done with my almost done with my discussion today. The last slide here is about performance assessment of these regularized models. Like we do for every model, we have to always check the model performance. So we try to look at the model performance of these regularized models, which is Lasso and Ridge, using less number of subsets compared to the normal linear regression. For each model, we examine if the number of predictors have reduced as compared to the ordinary least regression. So that's one of the objective we have. Is that really happening or not? In Bayesian Ridge, one of the techniques that we have there, we could also look at the regularization parameter that it provides. It throws out a value for what that regularization parameter is. And that tells us whether the model is applying low, moderate, or high levels of regularization. If it's applying high levels of regularization, that means it believes that there should be large weights that needs to be penalized, right? So there's something which tells us that that model is indicating that it tries to reduce the number of predictors. Normally in business context, the reason why these are important is because we have so many predictors that we need to identify them. And some of these predictors are highly correlated with each other, right? So sometimes the age and income is highly correlated, and which one to use and which one not to use. So all these things become extremely important in large data sets with a lot of variables where these variables are highly correlated with each other. It is very important to then determine which subset of variables we should be using, and hence models like regularized models or all those techniques that we looked at become important.